Welcome, EBS viewers. My name is Professor Brian Schmidt, and I'm here at the Australian National University's Mount Stromlo Observatory as part of the Great Minds series. And today, we're going to talk around what is in the universe, because we want to understand why would the universe be speeding up over time. And through general relativity's predictions, we know we need to understand what is in the universe and how much to figure out the trajectory of the universe. Those are the important bits of general relativity's needs to make predictions of the universe. So asking the question of what's pushing on the universe, the first thing that comes to mind was Einstein's mistake. Back in 1917, remember Einstein, to balance the universe out, came up with the idea of what he called the cosmological constant. Energy thinly spread throughout the universe. And this energy in his equations of gravity causes gravity to push rather than pull. And so it turns out by adding the cosmological constant as an ingredient in the universe, you can naturally create the acceleration over time. And so I always like to say that it seems like Einstein's greatest blunder is my greatest discovery, such as the wonder of Einstein. So with Einstein's theory and the cosmological constant, we can go through and we can ask ourselves, how much of this stuff do we need? Now, this stuff we call the cosmological constant, or often, because it might be a little different than what Einstein came up with, we call it dark energy. So why do we call it dark matter and dark energy? Well, astronomers, whenever they don't know what's going on, seem to revert to the word dark, because we can't see it. Dark matter we've known since the 1930s, and Fritz Zwicky gave it the name Dunkel matter, dark matter. And it was because it was invisible, dark energy. It's energy that we can infer is everywhere in space, but we can't actually see or measure it. And so dark in astronomy means essentially undetected. And it shows ignorance. So it is probably one of those things that we use when we're a little bit ashamed of our state of knowledge. In all cases, it's energy spread throughout space, but it's whether or not it stays exactly the same over time, or whether or not it changes over time. That is the question. But if you go through and do a detailed analysis to our supernovae and how their brightness and redshift looks back in time, we find that the universe needs to be a mix of 30% gravity that pulls, the normal stuff, and 70% gravity that pushes. So that is a prediction that we can go out and test. And it turns out when we made this measurement in 1998, there was already an experiment using galaxies, also done here at Mount Stromlo, what we call a redshift survey, to go out and measure how much gravity that pulls is in the universe. And the idea is that you go out and you look at how many galaxies there are with different redshifts, and you make a map, a redshift survey. And in 2002, the Anglo-Australian Redshift Survey went through and mapped out 221,000 galaxies. And they make a foam that was seen, for example, in the CFA Redshift Survey for the first time when I was in graduate school, and has been taken to the nth degree, for example, by the Sloan Digital Sky Survey since. But this foam tells you about how gravity has taken the the universe after the Big Bang and formed the galaxies in the universe. And it turns out that depending on exactly how much stuff there is in the universe, you can go through and get different foam structures. And by looking at the structure of the foam, you can judge how much stuff there is in the universe. And in 2002, they discovered that the universe was about 30% to the way of being just right, of being flat, with material that has gravity that attracts. So that was a measurement made in 2002. But these experiments were blind to gravity that pushes. They just couldn't tell if it was there or not. One of the other things that those experiments demonstrated is that there was 6 times more gravity that pulls than atoms that we could see. And so there was the concept that we needed something like dark matter, material that has gravity just like atoms that we're made out of, but is invisible. We think this material should be able to go right through, for example, the Earth and us, but still have gravity. Now, another experiment that came out and allowed us to look at this in more detail was an experiment based on something called the cosmic microwave background. In 1964, it was realized that everywhere in the sky there was a glow of radiation. Now, this radiation was in the microwave regime, so like what you would use to cook your vegetables at home. And this was discovered by Penzias and Wilson as the afterglow of the Big Bang. So when the universe was very small and hot, it was dense, and it was filled with light. And this light cooled and stretched as the universe expanded. And at some point, about 300,000 years after the Big Bang, the universe went from being hot and glowing like a hot bed of lava, and suddenly it became transparent as the hydrogen atoms grabbed their electrons. Before this time, the electrons were out on their own, free, and electrons turn out scatter light. And so light trying to travel through the universe was bouncing from electron to electron. And so that makes the universe look like a giant glowing bit of fog. 300,000 years after the Big Bang, the electrons could be grabbed on by their hydrogen. That's because the temperature of the universe cooled to 3,000 degrees, and the universe went from being opaque to transparent. So we see that afterglow of the Big Bang, and when you look at it as measured by the WMAP experiment and now the Planck experiment, you see ripples. There are tiny little ripples, and those are actually sound waves left over from the Big Bang. And those sound waves allow us to measure very accurately what the universe is composed of. And that's because what the universe is composed of changes the wave action. Now, the Big Bang was like throwing gravel into the universe, and so it made lots of waves. And the wave action depends on exactly what the universe is made out of, and so the splash mark of the Big Bang looks different depending on what the universe is made of, how many photons it has, how much dark matter it has, versus how many atoms it has. And so these experiments allowed us to measure how much of different waves there were, and you get a very complicated curve of big waves and little waves. And while it's a complicated curve, it can be predicted from physics that we understand here on Earth almost exactly. And I show, if you look at the curve as measured today, you can go through and you can see that in order to fit the curve, you need to have dark matter. And the ratio of dark matter to atoms is 6.5 to 1. We can measure that very accurately. If dark matter doesn't exist, it turns out you can't fit the early universe, the cosmic microwave background, at all. And so this is where prediction is manifested in what we see. And this is why we believe in cosmic microwave background. Observations tell us that dark matter is real. Now, other people have tried to come up with other experiments, but none naturally show this acoustic or the sound waves of the early universe well. And this experiment was predicted effectively from our observations back in 1998 of the supernovae. And what the universe model was predicted by our experiment has been essentially exactly replicated here as we've made better and better measurements. Now it turns out, well, it's kind of hard to use these experiments to measure dark energy. There is a way to do it. And that's because we can measure from physics itself the size of the waves exactly. And then we can see how big those waves appear here when they get to the Earth. And because space might be curved, we can measure quite accurately how big those waves are and compare it to the predictions of space being flat, that is just right, and light going out as perfect triangles, or space being curved and going on, for example, trajectories where the triangles have more than 180 degrees, such as in a closed, heavy universe, or less than 180 degrees in an open, infinite universe, a light universe. And when we do those measurements, it turns out we find that a universe that is just right, perfectly balanced between the infinite and the finite, that predicts exactly the size of those sound waves. So the experiment with the cosmic microwave background tells us when we add up all the things in the universe, it adds up to 100% of that necessary to be flat. The galaxy survey and the cosmic microwave background sound waves also tell us that 30% of that material is stuff that is where gravity is pulling, not pushing. So if we do a little bit of subtraction, we take the 100% that adds up to everything, subtract off the 30% of gravity pulling, we're left with that same 70% mystery matter, the stuff that's pushing. The same stuff that the Type 1a supernovae showed and inferred when we discovered that the universe was accelerating. So we live in a very funny universe. We live in a universe where 95% of the universe is stuff we do not see here on Earth. 70% dark energy, pushing the universe apart. 25% dark matter, invisible material with gravity, very similar to our own atoms, but invisible and seemingly able to travel right through the Earth and indeed through the galaxy. And finally, 5%, the atoms that we know and can study here on Earth. Now you may be thinking, if we have to invent 95% of the universe to explain what we see, maybe we just don't know what we're talking about. And that may well be true. but we are able to predict with very good accuracy every single experiment we've been able to do in cosmology with this crazy model. And that is what science is. Science is about what you think is right. It's about what predicts what we see. And so as long as this model is the simplest one we have that predicts the universe, we will continue to treat it as the best theory, the standard model of our universe. But we continue to look for ways that it might be wrong. How could the universe be explained with maybe new theory? Or maybe there's something missing? Or maybe dark matter does not exist at all? So in our next installment, we're going to think about how we might go through and measure with future instruments the universe, but also think about what the current observations mean for the future.